Tara, Devon, can you hear me? Hello? Hello?
Load.
You can't hear me?
Yep.
All right, excellent. All right, what are we doing today? First of all, let's take a look at what to do today. I don't think anything's due today. So it is the 10th. On our next class is the 15th, and on the 15th, the mod 6 is due, along with the error discussion. Did you all finish the error discussion last time? It was pretty easy. Okay. Let me take a look at it just in case. Let's see. Oh, before I go there, while I'm here, I'm just going to click on so, six error. Nope, nobody posted anything. No, I'm not sure, but nothing's showing up. Oh, now okay. Kara Devon. Okay. Kara's posted something about salary and BFFs. Okay, one thing you're gonna have to do, Kara, are you there?
Yeah, I'm here.
Okay, so this isn't useful because I see. No, it is A1. So 100,000 and 200,000 are two salaries that you've identified. Okay, that's good. So if I were reading this, I'd say at 200,000, a salary of 200,000, I have -8 friends. You know, maybe that's not a good one to use. 100,000 is fine. If you don't have any more people in your group, then 100 is fine, but -8 friends is bad. So at 100,000, you have about 5 friends, and you're pretty solid. The error is really, really small. It's plus or minus 0.03 friends. I don't know how big a finger that is, but it's not much. And then, and that represents less than a 1% error. And the reason why it's so low is because at 100,000, which would be up here, the derivative, this is why we need calculus, just so you know. The derivative here at 100, this is 100,000, it's right there. The derivative is this line right like that. And you might say to yourself, well, that's not close to 0. Or is it close to 0? This is 5, and this is 6, and this is 100,000. So these X values are super tiny, and the Y values are super spread out. Okay, I'm gonna tell a story. One time I was taking PChem lab, and my partner had this data that looked like this. Boom, 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 and she had a line going through it like that. Does that look good? It looks terrible, doesn't it? Like that line's supposed to go through those data points? No, but if you change the axis, instead of having it like 1.1 and 1.2 and 1.3, you actually made it this way, 1, then you have the data points actually look like this. 2, 2, 2, and the line goes through it. It's the same graph, they just changed the axis. You change the axis, it looks terrible. Okay? So one of the reasons why we need numbers is because we need calculus and we need numbers is because pictures can be deceiving. And in this case, that slope is actually close to 0. Okay. Any questions on that? Okay, I see who's in your group. Devon posted this. So this says, again, Devon, what is, oh, you want to go with the 20. Why didn't you tell us what A1 and B1 are? Because those are another ones. Those are, so 26 hours, you get a 99 plus or minus 2.65, which represents about a 2% error. Which you could see it's about 2% error, because if you're going to get close to 100 and it's plus or minus 2.5%, then that's 2.5% error, right? That's a good example. But maybe tell us what A1 and B1 are in case you want to know them. Looks like
Okay.
A1 probably a small number. You don't have to re-edit it. Just write it. Just add it. You know, edit it and A1 equals B. There you go. All right. Thank you, Jim. All right, next one. All right, so now here's this one. How is this one different from the other one? It's the same. You just posted it twice. Devon, did you post this twice because you have two different groups?
Yeah, I posted two different ones. One has a different number or variable in it.
You have 26 for both of them, don't you?
One of them should be 17.
17, wait, what? One of these is 17 and the other one's 26?
Unless I accidentally posted the same.
Look, if you tell me what A1 and B1 are, I don't care if they're exactly the same. It doesn't, because the other people in your group, they just can't say the same thing. You know what I'm saying? And you didn't have to do two posts. You could do one post and they could just follow off of it too. All right, I think that's it. All right. So the two producers are here, Kara and Devon. They're online, and then I have you three guys here. And who the other four people are. Okay. All right. Let's do this analysis of functions thing. I'm sorry they're not here because analysis of functions is kind of fun. All right. Should I take attendance now or wait till later? Okay. What? Later. All right, fine. So what is 0 times infinity? Oh, I did this survey. This was this is when I was playing with you know, those survey things that you could answer while you're in class. I said, what is 0 times infinity? So what is 0 times infinity? Is it? It could be anything. It could be anything. Do you want to vote for infinity? The last guy. Do I get it? Which do you vote for?
0.
I got 2 zeros, and it could be anything. Tara, Devon, which one do you vote for? A, B, or C? I'm getting it.
Infinity or 0.
Pick one. You have to pick one. 0?
Yeah,
two.
0.
Kara, what do you say?
Infinity?
All right, so I got one of each. Okay, here's the thing. Remember I told you, infinity is a really big number. And actually, infinity is not a number. The definition of infinity is not that it's a destination, it's a journey. You just keep making a number bigger and bigger and bigger, and you never get there. Okay? It's kind of like when people say they're going to come and visit you and they never do. It's sad, but it happens all the time. Don't tell me you're coming to visit me in a nursing home. But you know, come anyway. What? No, it's fine. Anyway, infinity is not a destination, it's a journey. Well, so is zero. You think zero is a real number that you can get to, but you can't ever get there. When I say any number, remember we talked about how fuzzy the number was? That was what differentials were all about. A little fuzziness to the number. So if zero is a little fuzzy, you multiply it by infinity. So let's say zero is not really zero, but 0.01. That's kind of small. What's 0.01 times infinity? Infinity. Okay. Let's say you try to get closer to zero by saying 0.001. Still infinity. Because infinity just keeps getting bigger. Because again, it's not a destination. It just keeps growing to match whatever you make zero, whatever number, tiny number you make zero, infinity will just grow to gobble it up. Okay. So it's not, it could be zero if you were absolutely at your destination. If you made it to zero, then zero times infinity would be zero. Would be. But since every zero is a fuzzy number, it's very likely it's more likely infinity. Okay. And again, if you have these are two destinations and one of them's halving and the other one's doubling, that is not changing anything at all. Okay. In other words, if your boss keeps doubling your salary, the government keeps taking half of it, then you end up making the same amount of money. Okay. Or if inflation eats it or whatever. All right, so the answer is actually C. Jake was right. Could be anything. What? No. Depends on how you're getting to it's remember I said zero and infinity are journeys. Depends on how you're getting there. If your salary is being cut in half by your mean boss, but you've opened up a business and you've doubled you're quadrupling what you make, then your boss cutting your salary in half, but you making 4 times, your journey to infinity is happening. Okay, because every time they're cutting you in half, you're just growing twice, you're growing 4 times bigger. But let's say your spouse spends 80% of what you earn and you make only 10% more each time. So you're growing by 10%, but they're eating 80%, you'll be bankrupt in no time. You should marry better. So what I'm saying, it's a journey. If you're going to zero because your spouse is spending all your money faster than you can make it, then you're going to zero. Okay. If you're doing really well in your business but someone keeps trying to take it away from you, but you keep doing well, then you're going to infinity. It just depends on what journey you're taking. Okay. If you're taking 2 functions and you're basically multiplying them together, you can have any number of functions. You can have 10 functions. But it's just a matter of which ones are going to infinity and which ones are going to zero and who gets there faster. And so what rule do we use to figure out what it really is? There was a rule we could use to find out what 0 times infinity is. For L'Hopital's rule, yeah. Okay. So it's interesting because I'm going to ask you these questions later. What is math? What is precalculus? What is calculus? What are the 2 rates of change? You need 2 points to 1 point. That's why we invented limits. And then limits were to find, we invented limits so that we could find the velocity, which is the instantaneous rate of change, or the derivative. Okay. You all know what the second derivative is? Yes. What's that? Okay, good. Because we're going to talk about that today. Okay. So if we're all about the derivative, what L'Hopital's rule is L'Hopital's rule says, okay, we're now going to use the derivative to figure out. So the derivative is like this. By putting a function on top of another function and saying how fast you're saying, and you get 0 over 0, both of those functions are going to 0. Question is, which one's going to 0 faster? So you can take the derivative of the top and the derivative of the bottom and say, how fast are you going to 0? How fast are you going to 0? And That's what L'Hopital's rule says. And then you can do that. And if it turns out that that's still going to 0 over 0, then do the derivative again. Or as long as you get 0 over 0 or infinity over infinity, you can keep using L'Hopital's rule. But the minute one of them's going off to infinity and the other one's staying at 1, then you're done. You know that this function's going to infinity. Or if the denominator is going to infinity, the numerator is going to 1, then you know it's going to 0. But you can keep using L'Hopital's rule until you don't have 0, 0, infinity, infinity. It's just a way to find limits. Again, you can use Desmos. Just plug in numbers if you want to know what the limit is. I know. All right. Let's talk about the next subject, analysis of curves. Okay. So this is my drawing. I tried to make it look nice, but I'd probably do better on Desmos. But so what I have here is, you see the black line here, that's the x-axis and that's the y-axis. And I have a graph, a regular old curvy graph here. It's probably a cubic. It goes down, it goes up, it goes down. And then look at the blue, this dark blue thing here. So the dark blue thing is a way of describing just the function. See, there's a dark blue y. This is what's the function doing? And all I want to know is plus numbers, 0 or minus numbers. So here, before this first 0, right? Let me get my just gonna get a pointer because it's better. Okay. See that right there? That's a 0. That's where the function is 0. At that line represents some point like -4. That would be a 0 for the function, right? There's another 0 there, and wherever that is, that could be like 1. And this one over here could be at like 10. Okay, and so I've just labeled them with little zeros in my box. Okay, and notice up here the function is above the x-axis, so that means it's positive. So I put a little plus there and I say above. Okay, then down here it's below, put a minus, then here it's above, and here it's below. Okay, this is basically how you do inequalities. You know, when is the function greater than 0, when is function. So that's just the function itself. That's the top bar. I do that in my pre-calculus class. Are we good with that? Okay, the next bar, we've been talking about the derivative. Okay, what about the derivative? Well, the derivative, the function is going down here, so the tangent lines are going to be negative. Okay, so even though the function is positive here, the derivative is that it's decreasing. This is like having money but losing it fast. Okay, this is like owing money and still losing it fast. And then you reach the bottom, and that's a minimum. So we have decreasing, it goes down. So it's a negative number, it's decreasing, the tangent is negative. The derivative is negative, the tangent is negative, it's decreasing, and then it reaches a minimum where the derivative is 0. Then what happens? I don't have any money, but I'm making money. So that's increasing. So I put a plus there. Till I reach a maximum where the derivative is 0 again. And then it comes down and then it decreases. Okay. So for the derivative, the pluses are where the function is increasing and the negatives are where it's decreasing. We've been doing this. We did this a couple times with our discussions, right? When you saw the derivative was positive, you said it's increasing by this much. It's negative, you said decreasing by this much. Okay, these max and mins are what we call critical points. Okay, so now sometimes I say max and mins, but I really should be saying critical points. Okay, that's the general term for max or critical number. The number is where the x, because they don't want to talk about the y value. The critical number is the x coordinate. Are we good with that? We've been doing that. We're comfortable with this. We're analyzing this function. Okay, so what about the second derivative? Okay. The second derivative tells how much is really how the first derivative is changing. If I am a negative, if my first derivative is negative and then goes to a positive number, is that increasing or decreasing? My first derivative starts off negative and then becomes positive. It's increasing. So it's what we call accelerating. Your speeds are increasing. So we call it accelerating, and the second derivative is positive. If we go from positive to negative, so I was doing some good speeding, and now I'm having to go back. What happens? Did my speeds increase or decrease? My speeds were decreasing. They went from positive to negative. So we call that decelerating. Your speeds are decreasing. It's like you're putting your foot on the brakes, you're decelerating. Okay, does everyone see that? Accelerating, decelerating, positive, negative. It changed from, you see all of these change from positive to negative, and then in between is a what? A zero, or maybe an undefined. But that's zero. What's that point, and where is it? And that's what we want to talk about. When did life stop being good and turn bad? Okay, that is called the inflection point. Right there. And it's got a particular meaning. So let's see. Done with this. Here it is on Desmos. Let me just so how do I see it? So when the second derivative is positive, or the second derivative is positive, it makes this U shape. You see the U shape in this curve?
Yes.
Okay. We call that concave up. So it looks concave and it's up. Do you see this other place where it's negative? That's concave down. And you see how it looks like the letter N? It looks like a piece of the letter N. That's how I remember them. Up looks like the letter U and down looks like the letter N. Do you see somewhere around that word where it says increasing? It changes from up to down, and that's where the inflection point is. Okay? Right. This is a real life example on Desmos where you can identify the zeros and stuff. It's very easy on Desmos to get the zeros. You just click on them, go click, 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 and it gives you the zeros, right? We all seen it? It's great. Maximum minimums, also Desmos, super awesome. You just click, click, it gives you the maximum minimums. You say, want maximum, and it gives you maximum. Want minimum. The problem is it does not give you the inflection point. I know. It's too much. All right, so how do we find it? Well, there's a few ways of doing it. We can look at the derivative. So here's a graph of the derivative. So that was the graph of the function, but this is a graph of the derivative. See how the derivative is positive, and then it becomes negative, and then it goes from negative to positive. Where it becomes zero, those points where the derivative are zero correspond to the maximum and minimum. Okay? So the zeros of the derivative, what's my talk? You know what? I'm going to get my own Desmos sheet now. Hold on. This Desmos is good. Let me put this function in. I have my locks on, so. No Suhabis here. Okay, so there's a graph of it. Remember I was showing you earlier, I don't like the way this looks, so I'm going to do this. I'm going to mess with the x-axis and go to only between -5 and 5. Oh. I want more y, so I'm going to make the y value go a little bit bigger. 70. Okay, all I did was play with the axis so I would see it a little differently. Actually, I don't want it. That's pretty, isn't it? Zeros here, here, there. Max and mins here and there. Now I'm going to, oh, I have to give this function name f of x. What? No, we don't know that. Maybe, but maybe not. So those are all the points we know. So let me graph the derivative and show you something. The derivative f prime of x. That's just a derivative. So now that's blue. We've seen derivatives graphed before too. Remember we did the mean value theorem? We graphed the derivative. See this 0 right here? It corresponds to, you see the x values are the same. See that? The maximum for the regular function is the 0 for the derivative. Look at this one. The 0 for the derivative is 6.88. Look at the minimum, 6.88. Everyone, are you with me on that? So what is it that Desmos can find easy? It can find zeros and what? Right, do you see the blue line? Is there max or min on that blue line? There is, it's right there. Oh, and look, you were right. The inflection point is exactly at 4. Okay, because that's where the minimum is on the derivative. So what does that mean? Okay, if I did the second derivative, you see I graphed the second derivative, it's negative and then it's positive. And there's a 0 right there. So when it's negative here, when the second derivative is negative, the graph looks concave down. It looks like the letter N. When the second derivative is positive, it looks like the letter U. It's concave up. And when the second derivative is 0, that's where the inflection point is. Okay. So inflection point can be found by setting the second derivative equal to 0, and you just, there it is. That's the inflection point. You want the critical points? You can get those by doing that. Okay, the derivative set equal to 0, that's inflection. Those are critical points, criticals. And the second derivative equals 0 and inflections. Okay. Not always true. There's also these things that are called undefined. Remember undefined stuff? Let me give you a function that's undefined for a second. Why am I getting the wrong things? Hold on. Okay, do you see this function of, see that function? Set the derivative equal to 0. Is there a place for the derivative equals 0? Let me just take the word criticals out. Does it find this? Nope. I see no graph because there is no place for the derivative equals 0. How about the second derivative? Is there a second derivative 0 anywhere? Nope. And you know why? Because what's the derivative? But you see a minimum, don't you? What's the derivative at that point? It's the slope of the tangent line at a corner. That's called a corner. We talked about them briefly. What's the derivative at a corner? Not nothing. Nothing implies 0. Do you mean not 0? Do you mean that there's some things? 0 and infinity are specific things. Undefined is another thing. Do you mean undefined? Oh, okay. Yes, exactly. It's undefined. So critical points are when 0 equals 0, and derivative equals 0, or it's undefined. Okay, so that's a critical point. All right. But the inflection point is not found by when it equals 0. Inflection point happens here. So an inflection point is when the concavity changes or the second derivative changes, or the second derivative changes sign. So let me ask you about the concave. Remember the u and the n thing? Do you see a u or an n here? No. So since you don't see a u or an n, the second derivative would be 0 everywhere here. Except, so if I graph the second derivative, watch this. I'm going to graph the second derivative. I'm going to graph it so you can see it. Y equals. Boop, do you see it? Here, it's right there. It's that green line. It's just 0 everywhere. Do you know where it's not 0? Look, this is the second derivative. 0, 0, 0, 0, 0, 0, 0. It's and right here at the bottom, it's going to say undefined. Undefined. See it? Boop. Undefined. Second derivative is not defined there because the first derivative is defined. You can't take the derivative of something that's not defined. Okay? But everywhere else it's 0 because the slope of the tangent line is 0. The derivative does exist everywhere. And the derivative is 0. The derivative is not 0 everywhere. I asked to see the derivative. Let me see the derivative. It's okay. Look, there's an interesting graph. The derivative is -2 all the way up to here, and then +2 everywhere afterwards. Do you see that? Because there's just, and then where right here it's undefined. This is discontinuous. Discontinuities are a great source of undefined. Okay. How about, let me try another one. Here's another one. See the function? Square root of that. All right. Where were the critical points? Is the derivative equal to 0 anywhere? No, but it's undefined. It's one place. Do you know where? Let's see. Here's the, oh, this is the derivative. Where is it undefined? It keeps going up, 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 but where is it undefined? At -2. There's no, you can't take the derivative of that little thing right there because it would be a vertical line. Remember, that's another time it's undefined if there's a vertical line. Let me make this the cubed root. It'll be a little easier. B over G. You know why I like the cubed root a little better? Because you'll see. Because the square root just ends. So the cubed root, see the cubed root has this shape to it, but at -2 right there, the tangent line is vertical. And we know that a vertical tangent line is not defined. So let's take a look at the graph. See, when I look at the graph of the derivative, the blue line, it's defined everywhere except there at -2. It's nothing. There's a vertical asymptote there. So there's no, not defined there. So that's why there's a critical point at 2. Or -2. There's a critical, its critical number is at -2. But is it a max or min? Is that point right there max or min? No, it's not a max or a min. Okay. But it is a critical point. So not all critical points are max or mins. This is, for example, one of them. What about the second derivative? What's that look like? Second derivative is also, it goes, but look at the second derivative. It goes from positive, no, so here the second derivative is positive. And if you look at the graph, you see how, what letter does that look like, a U or an N? That looks like a U. Now look over here, the second derivative is negative. And what's this look like? This side here, does it look like a U or an N? Looks like an N. Okay, so what is happening at that critical point? What's happening right there at 2, where the second derivative is not defined? What's happening? It's went from up to down. So the concavity changed. And what happens when concavity changes? You have a so that's the inflection point. But let me show you why that's an important point. If this were really a thing, okay, so if this represented, let's say, COVID, it's, by the way, it's not unrealistic for this to represent COVID. So let's say before they found the vaccine, the COVID cases were increasing slowly at first because, you know, they were in China, there was a handful of people, nobody got it, right? Then it started to grow really fast. Okay. And then what happens is a few things happen. But when it starts doing this, it starts to level off. This would be a point at which the inflection point would be the point where it was growing the fastest before it was the darkest before this, the light. It was going super fast up, and then it started to level off. Okay? Or slow down or whatever. That's why we want to know inflection points, because it's an important point. If bad things are happening to you, if you're in Florida and a hurricane is coming your way, making your life miserable, you want to know if you've reached the inflection point where it's getting worse. Okay? So here, if you think this is the worst of the storm, that's sad for you. If you think this is the worst of the storm, oh, that's still sad for you because there's more bad coming. When you get here, if you reach the inflection point, you know there's still more bad coming, but it's slowing down. Okay? So that's why we care about inflection points. We care about them in business. If your company is in a bad way or whatever, people care about inflection points. You know, I think yogurt. I think for some reason I always think of yogurt when I think of inflection points. So bacteria grows exponentially in yogurt. Do you know what yogurt is? It's kind of disgusting, actually. Milk that's left out.
Yeah.
That it's just left out, and nothing goes bad if it's left out unless there's something with it. Bacteria. So if you have bacteria, it'll go bad. So if you leave a cup of milk out with it just gets the bacteria in the air, whatever's floating around. If you touch the milk, the bacteria from your hand, and that's usually bad bacteria, and then it eats the milk and makes the milk go bad. But if you put in a culture, if you put in a good bacteria, like they do with yogurt, I think cheese is technically an enzyme, but it's like a bacteria. It eats the milk and it turns it into something edible that you can eat. And at first, the yogurt culture grows quickly. But then once it's eaten up all that it's going to eat, I think it eats lactose. I think so milk has sugar, fat, and protein in it. And the protein stays, the fat stays, the sugar's gone. People who are lactose intolerant can eat yogurt because the bacteria have eaten all the sugar. So once it runs out of sugar, the bacteria is it stops growing. Can't grow anymore because there's no more sugar. Okay? We did this second derivative stuff. So critical points are any points where the first derivative is either 0 or undefined. Okay, this is exponential. So this is a logistic regression that they use. Logistic regressions are used all the time for tracking diseases and like spread of diseases and populations that are starting to reach, like the yogurt is starting to level off. They want to know when the yogurt's starting to level off. Okay. If the yogurt's still actively growing exponentially, then there's still lots of lactose there. But once it starts to level off, the lactose is that it's running out of sugar and it's starting to finish up. By the way, the bacteria, correct me if I'm wrong, biology people, but the bacteria alive culture means it's still in there. Still alive. Maybe it doesn't have much to eat. Maybe there's no more lactose anymore, but it's still there. If you put it into new milk, you can make new yogurt from older. Do people not like yogurt? Do you like yogurt? What type of yogurt do you like? So if you got that Greek yogurt and you took a glop of it and put it in some milk and warmed it up, you would make more Greek yogurt. I know, because if you get your fingers in it, then you're also growing the bacteria that's in your fingers. So you have to be kind of careful not to contaminate your yogurt culture. Anyway, all right. So note the max and mins are when the zeros are the zeros of derivative. We went over this. The first derivative test. Okay, so this is okay. So these tests are interesting, but they're old. So the first derivative test is this. If you took the derivative of a function and set it equal to 0, that would tell you where the max and mins are. And it's not so bad. Sometimes you have a graph you can't see. You guys just don't know where the max and mins are. So if you take the derivative, if you can take the derivative of it and set it equal to 0, then you can be like, oh, there must be a max and min at those points, so wherever they are. But you can't be sure. You can only know that they're critical points. So if you take the derivative and find out where they are, whether 0 or undefined, you still can't know whether it's a max or min, but you can if you do this. The first derivative test is, if you have the first derivative, look here, there's a picture here. If you have the first derivative going up, before the first derivative, it goes up, and then afterwards, the first derivative goes down. So the first derivative is positive, then 0, then negative. Picture this in your head. Up, and then down. Is that a maximum or minimum? You go up the hill, and then you go down the hill. Was that the top of the hill or the bottom of the hill? The maximum. If you go down the hill and then go up the hill, was that the top of the hill or the bottom of the hill that you went, or valley? If you go down the hill and then go up the hill, that's a minimum. Okay, that's the first derivative test. That's what the first derivative test says. All right, the second derivative test is slightly different. It just says, find the critical points. So I found a critical point. I don't know if it's a valley, if it's the top of the hill or the bottom of the hill. But I take the second derivative at that point and I say, what's happening at this? What's the second derivative look like? And if the second derivative is positive, then it's what? Then what's the shape of the curve? It's concave what? Second derivative is positive, it's concave. Up. Up. So is that a minimum or maximum? If you're at a critical point and and around you, it's concave up. So you're either at a max or min, but everything around you is up. Are you at a minimum or maximum? You're at a minimum. You'd think it's a maximum because it's positive, but no, if everybody else is better than you, then you're at a minimum. What about if it's concave down? Everyone else around you is worse than you. Are you at a maximum or minimum? Maximum. That's what the second derivative says. So here's how it's done. You have some function. This is just like x cubed minus 3x plus 7. Then you take the derivative and you get this and you set it equal to 0. And then you solve that and you end up with 1 and minus 1. Then you take the second derivative, which is 6x, and you plug the 1 in. You plug the 1 in, you get a positive, and that's concave up. So that's a minimum. You plug the negative 1 in, you get negative 6. So that's concave down. So that's a maximum. So positive 1 is going to be, so positive 1 is a minimum and negative 1 is a maximum. So this graph is going to go, see if I can write it. Which comes first? Negative 1. So negative 1 is a maximum. So this graph is going to go up to negative 1. It's going to go down to positive 1, and then it's going to go up. Look something like that. So x cubed minus 3x plus 7 is going to look something like that. Only more curved. Okay, that's how we use the second derivative test. Again, you don't have to use the second derivative test because you can literally just look at the Desmos graph and say, I see a maximum. I see a minimum, and that's it, you're done. Okay. So I don't generally cover this as much as I used to because you can just see it. If you know how to adjust your graph. The only time you can't see it is if your graph is messed up. Okay, like for example, you know, I would never make you do it algebraically anyway. Let's take a look at this. Do you want to do it algebraically? I think on the homework it doesn't. I show you how to do it algebraically. I might ask you about doing it algebraically, but you're not going to do it. Maybe. Here's a graph. Where's the maximum here? I don't see it. Boo hoo hoo. But I could take the derivative and set it equal to 0. Look at this. If I set the derivative, there's the derivative. Oop, and I see that it's undefined at -2. So that must be where the critical point is at -2. Okay. And if I do the second derivative at -2, it's undefined. So that doesn't tell me if it's a max or min or not. Okay. But if I put a number, so I can put in a number less, I can put in a number like -2.001. That's a positive number. So I know it's concave up. One number's less than 2, and a number is bigger than -2, which would be 1.99. I know it's down. So I know I have an inflection point. It's undefined, but that's an inflection point. If I do the same thing with the derivative, so let me do the same thing with the derivative. If I put the derivative in, I have a positive number there. So after 2, it's increasing. And then before 2, it's increasing. So it's increasing and increasing. Is that a maximum or minimum? If it's increasing, and if you go up the hill, reach a critical point, and then keep going up the hill, is it where you were? Is that a maximum or minimum or neither? It's not gonna. Okay, and if you look at this graph, you can see it. It isn't, it's a neither. Oh, you can't look at the graph. Why can't you look at the graph? Because I just put it up there. Let's just take it down. Bring it down. All I did was raise it up to 5 million. But I can just move out. And eventually, when I get to 5 million, I'll see it. There it is. I can't see anything now. I've ruined it. By adding 5 million to it, I've lost all the pretty. And so anyway, that's what I'm telling you. Doing the first derivative, like knowing, you know what the first derivative is, and you know stuff about it, you might be able to tell, even though your graph is completely unworkable. Okay. But as far as algebra goes, I don't think that buys much of anything. If you have a graph as simple as this, you can just see it. If you have a graph that's a little harder, you probably can just adjust the graph until you see it. If you have a graph that's impossible to see, you might have to do the derivative stuff. Okay. All right. So an interesting thing about regressions, the linear regression is a line. It has no critical points and no inflection points. Okay, you understand the line has no max or mins, and it has no inflection points because it's concave 0, because there's no concavity. An exponential graph is concave up or down everywhere. So it too has no max or mins, and it too has no inflection points. So exponential, no. Logarithmic, same thing. It's not going to have any critical points and it's not going to have any inflection points. A sine regression that goes up and down like this, that's crazy. It has max and mins all over the place. It's critical points regularly placed, and it has inflection. It goes concave up, concave down, concave up, concave down. So it's got lots of everything. Quadratic, cubics, and quartics, they have quadratic has one less, quadratic is a parabola. So it has one critical point, and its inflection has one critical point and no changes in inflection. So there's no inflection point. A cubic has 2 inflection points possible, and 1, 2, and 1, 2, and 1, 2 critical points, 1 inflection point. A quartic can have 3 critical points and 2 inflection points. Can have. Doesn't have to, but it can. So for example, how are you gonna know? When you look at, you can look at a table and what you can see is they change sign. Remember I talked to you about that rule, one of the theorems we didn't really go over well is, intermediate value theorem. So I just have a table here with numbers on it. So between 20 and 40, you look between 20 and 40 on the X, you'll see that the y2 is the first derivative. You see how it went from positive to negative? Okay. That means there's a critical point. That means there's at some point between 20 and 40, there's a critical point. And if you look at y3, it's always negative. If you find a critical point and it's always negative, the second derivative is concave down, is it going to be maximum or minimum? Between 20 and 40, there will be what? A maximum or minimum if it's concave down, the letter N. Devon, concave down, maximum or minimum? Oh, Suhabe's here. Suhabe, concave down, maximum or minimum?
Maximum.
Yes, concave down is a maximum. Look at between 120 and 150 on the X. You see how the derivatives are also, they're going from negative to positive. Okay. And you see the second derivative is positive. So either the first derivative test or the second derivative test tells you that what's happening. The second derivative is positive. It's concave up. Is it a maximum or a minimum? Name out. What is it? Maximum, minimum. If it's concave up, like the letter U in up, does that have a maximum? Yes, Sarah saying it has a minimum. Minimum? Is that what you're saying?
Yeah.
Letter U has a minimum. So this is a maximum and a minimum. Then the next thing here, it does have another one, and it's probably another maximum. Okay. Now, for looking at inflection points, we look at the second derivative. Do you see how the second derivative changed between the numbers 7 and 8? It changed, and it also changed between 9 and 10. So that means there's an inflection point between 7 and 8. There's an inflection point between 9 and 10. Okay, I'm looking, it's hard to see this because it's the old calculator, but if you see a little minus sign, it's negative. You see no minus sign, it's positive. It changed signs. That's what I'm looking for. When things change signs, then, you know, there's a good chance. So let's do this on Desmos. Let's create a function. Ooh, look at that. I don't see hardly anything there. So looking at that, if I create a table, do that table thing where we do f of x1, f prime of x1, and f double prime of x1. Okay. If I just put a bunch of values in, to shoot, I wanted. Okay, looking at these numbers, they're all what? Positive all the time. Right? So from 2 on, it's increasing and it's concave up. Okay, but I want to do some other numbers. So I'm going to do -5, -52, -5, -4, -3, -2. Let's see. Okay, so now what do you see? You see that the function has a 0 somewhere between 1 and 2. Yeah, there it is, 1.09. Fine, don't care about that. Are there any zeros for the derivative? Do you see that? Has that ever? No, it's always positive. You see how this graph is always increasing? It's always positive. How about the second derivative? Anything, do you see an inflection point and where might it be? Oh, it's blatant where it is, because here it's negative and here it's positive. But look, it even tells you it's 0 right there. So that's where the inflection point is right there. Okay. So that's what I'm saying. We can use these tables of numbers if we have to. But I'm not a huge fan of this. Let's see if this were a fourth power. Okay, what do we see there? I see a 0. I see the 2 zeros, right? They're at negative 1.3. Like there, between the 37 and the negative 6, and between the negative 2 and the 45, there's another one. Are we good? Do you see a max or min here? Does the derivative change sign anywhere? Yeah, somewhere between negative 1 and 0. That would be that one right there. How about inflection points? Are there any inflection points? No, there's one for sure. Right there at 0.
Exactly. It's an inflection point, interesting.
Well, here's what you don't see. Let's find out. It looks, there's a minimum right there. But it says there's an inflection point. But this line looks awfully flat. Like the derivative, like the second derivative could be 0 in a lot of places, but it probably isn't. Let's just ask, when is the second derivative equal to 0? Oh, maybe just the one time. Okay, so what happens there? It's concave up here, and then it flattens for just a second, and then it's still concave up. So this is really not an inflection point. Even though the second derivative is 0, it's not changing sign. It went from positive to positive, so no, not an inflection point. You can see it's not really an inflection point. It's just that the curve, it was curving like this, and then for just 1 second it went flat, and then it curved again. Usually there's more than one, though. I really was hoping there would be 2. Sometimes you can't see them. Let's see if there's more than 2. So this is what I'm going to do. I'm going to take this function. Can we find the derivative of it? So now I have to do algebra. I said you wouldn't have to do algebra, but I like 12x raised to the third plus 2. Okay? I don't want that. I want the second derivative. So what's the second derivative? Okay, now if I set that equal to 0, what's the solution? Just 0, right? It really only has one solution. It's repeated twice. So yeah, thought there would be 2, but I was wrong. If this number here, if this had been raised to the third power, like that, I would definitely have had more than one inflection point, I think. Hold on, let me see. What I have? So I just changed the function. Take a look at it differently. Okay, so now what I see, okay, so look, I changed the function to something else. So I changed it to this. I see there's a minimum here, somewhere around 0, there's a minimum. But do I see any inflection points? No, not really. But when I go and I say set the second derivative equals 0, look, I got 2 answers. Where are they? Where are those answers? I think if I change this to just set of equal sign, I do that. That's the second derivative. I just click on them. Minus a third and 0. So the problem with our table is that we went right over minus a third and 0. Look, we were at minus 1 and then 0. We didn't do negative a third. So what you'd have to do is try minus 0.5, minus 0.3, minus 0.2, minus 0.1, 0, Do you see now that this, you see how it changed sign? It went from concave up to concave down to concave up. And generally what that looks like in a bowl, it looks like a dent in the bowl. To see how it was a U, and then for a little bit it's an N, and then it's a U again. Okay. Okay. So this one right here, see how this, a lot of you, when you're doing your project and stuff, when you're doing your stuff, you'll see a dent in your quartic regression. Then you'll have two inflection points and a critical point. One of the things you have to do for this particular one that we're doing the analysis of function, which is due next time. I mean, it's not due next time, it's just error, but the time after that. Analysis of functions, you're going to have to make sure you have at least one max and min, one critical point that works, and at least one inflection point. It's possible to have one or the other and not both. Okay, in which case you have to do two regressions. The quartic will always have a maximum or minimum. Quartic will always be either have a concave up or concave down part. But a cubic doesn't have to. A cubic may not have a maximum. The cubic will always have a cubic function should always have an inflection point. Quartic won't necessarily. Okay. So do you understand what I'm saying? Why is that? Let me, I don't see it here. It should just example sometime. Okay. Okay, stop. Let me just show you why they do what they do. Okay, a quartic can go down, it can go up, it can go down, it can go up. That would have three inflection points, but can also just go down and come up. Not inflection points, it could have three critical points and two inflection points. But if it just goes down and up, it doesn't have any it has a minimum, but it doesn't have so many inflection points. Do you see that? Minimums, both of these have minimums, no inflection points. What can a cubic do? A cubic can go up, it can go down, it can go up. In which case that has two critical points and one inflection point, right? That's great. If your graph looks like this, great. But cubics can also do this. They can go up and they can level off a bit and then you can go up again. Does that have an inflection point? Oh, that does have an inflection point, but it doesn't have a maximum. So there's an inflection point somewhere around here for both of them. Inflection point, inflection point. There's a max and min, but no max and min. Here, there's an inflection point, inflection point. If you're lucky enough to get it, and you have three maximums, 1, 2, 3. But this one only has one. So if you have a graph that looks like a U, or I call that a jig, you're going to have to do both of them. So if your data, and the problem is if your data is very linear, like a line, like if you're doing world population or something, it would be very difficult. But you're not doing anything. The BFF group, who's the BFF group? It's not you. That's business groups, BFF group. But their data is not linear. Is your data linear? You are the, now, linear data tends to give you problems. But as long as you have a quartic or something that goes up and down or whatever, then the cubic will also go up and down, and you'll be able to find that. Okay, so why don't we try that in our groups now? If you don't have stuff to do from last time, might as well start the next one. So all you have to do is find the critical points on your graphs in your real life data. Hold on, I have to get else go. So here, Kara, BFFs, you have a critical point somewhere around here and somewhere around there. And all you have to do is you go down to the part of your graph, which is analysis of functions. Here, this is the whole thing where you have to find them all. So you can, so to find them all, you only have to graph the derivative. And if you look for the zeros of the derivative, that'll give you your max and midpoints. And if you look for the max and mins of your derivative, that will give you your inflection points. And that those numbers go in here for, you don't use A and B, use whatever numbers you have. Okay, so for you guys, I know for Kara, you're gonna have 5. I don't know about the other group. Let's see, who's the other group? Devon, did you give me a link to yours? So Devon, you are going to have. Okay, so what do I see in his, what do we see here? How many max and mins do you see? Just, I don't know. This is so weird. So let's take a look at analysis functions. If you graph the derivative, I see a 0 there, but is there another 0 here or isn't there? Oh, there isn't. How close. If it had been just a little bit lower, you would have had 2, you would have had a max and min here, but you don't. So this graph doesn't have a max or min. How about inflection points? How many inflection points? Doesn't this look like a U with a dent in it? So it's going to have how many inflection points? 2, and that will correspond to this point right here. Actually, there's more than 2. There's 1 here. There's an inflection point here. But there's also an inflection point wherever this minimum is. Find the minimum. There it is. There's an inflection point there. Okay, let's break up into our groups. So both of your graphs will be fine. You don't have to do more than one regression. Is what I just checked. So let's go for it. If you have a group that's big, like Sarah and Devon, you guys could break up your max and mins from your critical points and everybody can say something different. All right, what am I doing? Breakout rooms? You know what breakout rooms we have from last time?
I have a question before we break up.
Go ahead, Tara, what's your question?
Is this for mod 7 or is it still mod 6?
It is not for mod 6.
Okay.
Open up mod 7 so you can post it. Sure.
Thank you.
Open up mod 7 and pop it there. By the way, that's the last, the reason I'm trying to get it over with is because it's the last discussion before the midterm is mod 7. So then the midterm is on all the material up to mod 7. So we can talk about it some more. Anyway, the rooms are open. Put yourself in them. People who are here, you want to log on so that you can be with your room.
Sure was one.
I don't remember. Check what room were you in? Were you business or science? Kara, your business, what room were you in last time? I think business was in 1.
Yeah, we were in 1.
Okay, so Kara's going to 1. Mahira, you in which group are you in?
First one.
You're in business? Devon is in 2. Suhabe is in
Business.
business? Okay. That makes it easy. All right, so now, Mahir, you've signed up with your business group. Suhabe hasn't joined yet. You guys, I see Sarah, Nina, and Devon. Jacob, you're not on there. You don't have to be if you sit close to her. Or you can just be that. You can zoom and not have to be anywhere near her. It's up to you.
There's our group. Right now, we only have 4 people in our group.
Oh, you'll have more to post. This is for a week and a half away. So someone's gonna show up sooner or later.
So we make 2 groups.
No, make one post and make them suffer.
So it's 1.
You can just do the regression that you have. If you want to do a different regression, I can show you how to do a different regression, or you can break it up with the people who are here so that one person does the math for a critical point, one person does the math for an inflection point, one person does the words for a critical point, one person does the word for an inflection point. And then you have Nana in your group, she can say it all. She can present it. That's an interesting idea. You know what? I should do that in the future. I should make sure every group has one producer and one presenter, and everyone else I don't care about. The presenter's not going to be happy if the people don't say something, though. She won't have anything to say. I'm going to do that in the future if I teach again. Okay? What? I'm going to open up 7 for you now. If you have anything to fix in 6, do it. I'm making 7 available, but there's not anything in it, but I will put the questions are there, the homework is there, there's a video. There's the analysis discussion, so let me just create. Wait, not yet, I'm doing it right now. What is this called, analysis? That's right, you stick it. It's easy enough to produce. Are you guys talking about anything here? I'm gonna join this group. I suspect Tylee is. Okay, so here. I need to go to lesson, what did we just go over today? 5 or 6, 6? So if I go into the error line and I click on Devon Hales, it needs to be linked. Thank you, Devon. Anyway, what I do for the analysis of functions is I graph the derivative. Okay, let me change the color. Oh, careful, this purple color. Okay. Then I click on 3 things. This one right here, minus 1.86, and I put that in the table. Minus 1. Put that here. Then I don't see any other, but I look for a maximum, which is here, 5 point. So I highlight that. Put that in the table. So then I go around here and I find that last one, whatever that is, 19 point something. I put that in the table. Interesting. It took those two and it figured out what the difference was and it gave me another point. Okay, so now you have enough information. So look, for this one, the derivative is 0. And the second derivative is positive. What's that? The derivative is 0, and the second derivative is positive is what? Minimum. So for 5.4, the second derivative is 0, so what's that? At 19, what's that? The second derivative is 0, so it's 1.
Inflection curve.
Right, yeah. Second derivative is 0 is an inflection point. Look at your graph. Look at not the derivative, not the red line. Now look at the graph. Do you see a minimum here? You do. And you see it somewhere around here is an inflection point. There's another inflection point over here. See, here it's concave down, it's like the letter N. It's a U with a dent in it. So that's what he needs to put in those tables. I don't know what he's putting there. It's a table. Javon's tell him that because I'm not sharing screen with him because I'm not in your group.
Yeah, so basically.
But he could have looked at it because if he was looking at us, that I was just doing it right there on the screen, was I not?
Yeah, but it's not, he's in a breakout room, so you didn't see the screen.
Oh, that's true. Oh,
Um,
so pretend like you came up with all that.
um. Um. I think
I think you're muted.
I'm not saying anything,
Oh, sorry.
but I was muted. Thank you for, I was just getting set up. Giving you a minute to get everybody back from the breakout rooms. Five. There's 5 online and there's 3 people here. Who's missing? Well, I'm gonna know this because I'm gonna do this. All right, before I get started very quickly, I don't have a lot of time, but I'm gonna ask the same questions I asked before. Actually, they're not the same questions. Suave, how many points do we need for instantaneous rate of change? Instantaneous.
1.
Good. It's not here. Sarah. What do we need for continuity? Wow, very good. Jacob. What are other ways of saying instantaneous rate of change?
Derivative velocity, so the tangent line or dy over dx.
Devon, what's the derivative of a constant? What's the derivative of a constant, Devon?
0, sorry, 0.
Sarah. What's the derivative of x to the nth power?
N times x to the n minus 1.
That's the power rule. Mahir. What's the product rule say?
Product would say,
Yep.
first times the derivative of the second plus the second times the derivative of the first.
Okay. Nina, I know you've had this before. What's the quotient rule say?
Denominator times the derivative of,
Numerator.
I can't explain it. Denominator times derivative of the numerators over denominator squared.
Yeah, that's good enough. Nina. What? Oh, that wasn't even, sorry. Anusha's not here. 12. Melanie's not here. That's another person who's not here. All right. Let's go back down here. So I didn't ask any of the ones from this week, but let's see what they say. So the ones from this week are. When can we, okay, so what is 0 times infinity? Anyone want to answer that question? Asked it already. What is 0 times infinity? I'll ask Jake. Jake, what's 0 times infinity?
Can be anything.
Depends on the journey.
That's on the journey. When can we use L'Hopital's rule? When the limit is 0 over 0, infinity over infinity. What is acceleration? We already had that question, but what is an inflection point? Yep, it's when concavity changes. And what's a critical number?
Maximum.
Or when the derivative is not, it's when the x value is where the derivative is either 0 or undefined. So it could be a critical number, doesn't necessarily have to be a maximum. Could just be where it's undefined. Okay. But so a inflection point has to exist. And so the second derivative could be 0 and it won't be an inflection point. But it's kind of weird. So an inflection point is only when the concavity changes. So, but a critical number is where the derivative is 0 or undefined. In there will be max and mins. All right, so for homework, you have a limit. I don't care how you get those answers, limit. But if you look at them, you should look at them because it'll explain how L'Hopital's rule works. Because you might see a L'Hopital's rule on the test, on the quiz, say, what happened here? And you just say L'Hopital's rule. Okay, the next group of questions was determine where the graph is concave down. So if you just type in, if you want to know when it's concave down, what is that? This concavity is which, the first derivative or the second derivative? Second derivative. And you want to know when it's down, so if that's a positive number or a negative number. So is it less than 0? And you do that, and you can either solve it or Desmos will just show you the answer. There's the answer right there. Everything less than negative 6.5. Okay? So Desmos gives you for a shade, if you want where is it something, you want a region, you can just do greater than or less than, and it will show you a shaded region. Okay? All right. Find all critical numbers and use the second derivative test to determine, so you can read about that. So if there's going to be, for this one here, there's probably only going to be one critical, oh, there might be more than one critical number, I'm not sure. Might just be one critical number. All right. The interval where the S of X is concave up. All right, so let's try the same thing. What do I do to find out when it's concave up? Second derivative is what? Up. Positive. Okay, don't confuse. See, max and min and up and down are completely different. Concave down is this. It's sad, but it's a sad face. But it's a maximum. It has a maximum. A frown has a maximum. A smile has a minimum. And that's the confusion. Concave down is sad. It's got the letter N in it. N. It's sad, but it has a maximum. Concave up, it's a minimum.
The graph is simpler.
Can be. But for this one, it was particularly weird because look, if you want it greater than 0, it's every number bigger than 0. But if you look at the graph, it's going to be hard to see it. So if I look at the graph here, hard to see where it's differences to where it changes to concave up. It's very smeared here. But it's definitely up here and it's definitely down there, but it actually happens at 0. That's a difficult one. Okay, how about this one? I think that's all of them. There's this one's, the algebra here is very painful. But if you just want to know when it's concave up, just type in T of X with double prime and say greater than 0. It looks like everything, so you have to find those 2 lines there where they are. Okay. You can find those 2 lines by setting it, by just graphing it like that. That's the second derivative. And there's one here, and there's probably a vertical asymptote. It's undefined at 0. Okay, so I'll let you muddle through those. They're okay. So you can do it algebraically. The homework does it algebraically, but you can also use Desmos to find the answers. Sure, if you can, because sometimes it's a little hard to see, and you might want to use Desmos. You might want to use the algebra if you can. Okay, any other questions on this? It's 5:30. I'm done. You have the homework. Oh, one last thing. Let me just quickly look at the quiz for a second. You have the quizzes due next week. And the quiz has questions. What am I looking for? Quiz 6. Where is quiz 6? Quiz 6 didn't show up. Should have been up by now. Hold on. Yeah. It's course completion, yes. Due date is when next Tuesday, 15th. I know I did this, maybe I didn't have. Alright, so now quiz 6, now it shows up here. There we go. Quiz 6, let's take a look at it. So, things you might be asked is, what is 0 times infinity? Saying this out loud, so now this is just saying a limit out loud. I was going to change this, that's why it wasn't up, because differentials are really what I asked you to say. But this is just a regular limit. And it doesn't even say the function with quantities and everything, so. Question 3, determine the inflection point. Okay, the number 6, so let's take a look at this. 5 and 6. 5 and 6, what happened here? They said that, look, the second derivative less than 0. So what are they looking for? Concave, up or down? Down, concave down. Okay. Term graph is concave down. Okay. Find a critical number. So you just take the derivative, you just find it. For this, you can just graph it and find the max and mins. Okay. Or you could set the derivative equal to 0. And then, of course, this is, yeah, so now this is analysis of functions, it's not error. Huh. It says, it's according to the blank regression, there's a relative maximum at blank and a relative minimum at blank. So this quiz is actually kind of odd. I may have to fix it. Don't spend too much time on it because I might fix it. Okay. That's all. Have a good day.